Hey guys, welcome to another video for chemistry. In this video we're going to be working out some of the review problems in the chapter assessment in your text. And so you'll see that I have the screenshot there of what you have in the book. And I'll work out problems 48 through 55 in this video. Actually, I may break it up into two separate videos. I'll work out maybe 4 problems in this one and then the next 4 in the other. Just to keep the video at a respectable length, because otherwise it'll get super long. Keep in mind that you'll be able to fast forward, like if you have a question on 50 but not 48 and 49, then you can easily skip to that problem and see how that one works out. So in any case, I'm going to get started. So I'm looking at 48 and it says what is the speed? So what is the speed? So I'm going to be looking for speed of the electromagnetic wave with the frequency. So I've been given a frequency and a wavelength of 2.25 nanometers. So I have two givens in this problem. Okay, I have two givens. Number one is frequency, and that is 1.33 times 10 to the 17th hertz. And then I have wavelength, lambda, which is 2.25 nanometers, which is times 10 to the negative 9, right? So I'm looking for the speed of the electromagnetic wave. Now, speed, when it comes in this context, I know that the speed of light is 2.99 times 10 to the 8th power, so that I know that my answer should be really close to that, okay? But let me go ahead and confirm that. Now, given that these are my two givens, the best equation to use is my speed of light equation. So I take my speed of light equation, C equals lambda, which is 2.25 times 10 to the negative 9 times my nu, which is 1.33 times 10 to the 17th power. So, at this point you can pretty much put this into your calculator. You can put you can do open parentheses 2.25 times 10 to the negative 9, and then I can do close parentheses and then open parentheses 1.33 times 10 to the 17th, close parentheses, and I'll let the calculator do the math for me. In fact, I'll do that way first, just so you can see how it's put into the calculator. But then I'm going to do it, mental math, okay? Or at least putting it on Scratchwork so you can see how it's done that way. So open parentheses, 2.25 times 10 raised to the negative 9 power, and then we'll hit the arrow button, and then close parentheses, and then open new parentheses, 1.33 times 10 raised to the 17th power, arrow, close parentheses, and then enter. And then my answer is going to be it's going to be, I'm put it in red, 2,959,000. Actually, no, let me just write it out. And then 3 zeros. So, yeah, so then this is a big number, and I don't like big numbers, right? We don't want big numbers. These are just really awkward looking, and we want to make this into scientific notation. So 2, 3, 4, 5, 6, 7, 8. So that's 2.99 rounding 6 times 10 to the 8th power. Okay, and as you notice, it is very close to the speed of light, which is what I knew it would be, right? So yeah, so 295,925,000 meters per second, or 2.96 times 10 to the 8th meters per second, which is the speed of light. So that confirms that. So let me work this out in another way so you can see how you can do this mental math. And this is how I prefer to do it now because it's just easier for me anyways. It may or may not, but either way, I think it's important that you know how to work out these problems this way too. So the first thing I'm going to look at, I break this problem up into its constituent parts, which first I take a look at the power part. So I have times 10 to the negative 9 times 10 to the 17th. Now, if you recall the mathematical rule for multiplying numbers with exponents, if the number has the same base but a different exponent, Okay, as long as it has the same base like we do here, times 10 times 10. So what I can do is I can just have that base, and then I can add the exponents together. So in this case, it's 10 times negative 9 times 10 to the 17th. That equals 10 raised to the negative 9th plus 17, which is 10 to the 8th power, right? 10 to the 8th power. And so now I just need to do my next part, which is multiply these two numbers out. 1.33 times 2.25, which is going to be about, here, I can do it in my calculator. 2.25 times 1.33, and that is 2.99. So as you can see, that also gets me the same result. Okay? So I'm going to be working them out that way so you can see. So keep in mind this rule right here. Okay, this is a very important rule that you learned in Algebra 1 for the multiplication of numbers with exponents with the same base. All right? So let's move on to the next problem. So I'm looking at 49. And it says, what is the energy of the photon? So I know I'm looking at energy, so I can start writing my equation, energy. And it says of red light that has a frequency of 4.48. So here's another given. Frequency is my nu. So 4.48 times 10 to the 14th hertz. Okay, so, but the question was asking about energy. So then I need to go to my energy formula right there. All right, I need to go to that energy formula, and that is Planck's constant times nu. So I already have my nu, right? I already have that right here, so I can replace that with that. And I also know what Planck's constant is. So Planck's constant I know is 6.626 times 10 to the negative 34. So at this point, I can just do the math. So I can do 6.626 times 10 to the negative 34. Times frequency 4.48 times 10 to the 14th. So I'm going to work it out the same way I did before. So if you remember, I'm looking at my powers first. So it's going to be 10 to the negative 34 plus 14. Okay, and this will be negative 20, right? So negative 20. And now I have to figure out what comes in this box right here. And that is this number multiplied by this number. So let's go ahead and do that in the calculator. 6.626 times 4.48. Okay, so that's 29.68. Now you should see a problem with this number. And the problem is right here. This number is not between 1 and 10. So in order to make it between 1 and 10, I need to move this decimal over, okay, and I'll have a new number, and that number will be 2.968. Now, I moved the decimal over once. So when I move the decimal, that's actually going to change what I have as an exponent. It's no longer going to be negative 20. Now, I moved it over once, so that means the decimal point will only move over by 1. Okay, so keep that in mind. So it'll either be negative 19 or negative 21. Now, the way that I always found it easier to remember how it changes is that I looked at what I started with and what I ended up with. And I started with 29.68. And I ended up with 2.96, and that number went down. So I always remember that this term right here has an inverse relationship with that term right there, an inverse, so an opposite. So that means if my term went down, so I went from 29 to 2.9, so it went down, that means that my exponent will go up. It'll increase. And so it was a negative 20, so that means it will become a negative 19. Now remember, with negative numbers, increasing means going closer to 0. And if I think about my number line, with 0 being here, negative 20 is over here, well, if I'm going closer to 0, my next number will be negative 19. Okay, so just keep that in mind. So So if my term goes down, then my exponent goes up, and that's what happened there. So that is the answer to that one, and the unit for that is in joules. Okay. Okay. So do keep in mind that you can that you can always rewind and listen again and pay very close attention to what I'm saying and how I'm saying it. Okay. So I didn't mean to erase the Planck's constant. I want to leave that there. Why not, right? Okay. So let's move on to the next problem, and that is problem 50. So Mercury's atomic emission spectrum is shown at top. So this is the figure that I'm focusing on here. Estimate the wavelength of the orange line. So I'm looking at this orange line right there. Okay, I'm estimating that wavelength, and I'm going to go ahead and estimate it at 615 nanometers. Okay, so I know that this is what, 625, and so that would be 605, 610, 615, right? That's how I got to that point, 615 nanometers. So that's that, and then it says what is the frequency? So now I need to find frequency. And then another question, what is the energy of the photon corresponding to that? Okay, so I got a lot to figure out here. So it's asking for the energy, so I'm going to use this equation also, but it's also asking for frequency. I need to find frequency first, right? So I'm going to use my speed of light equation. Now I know I'm going to use speed of light because I've been given a wavelength, lambda. Right, so I have lambda, and I also have speed of light. Speed of light being 2.99 times 10 to the 8th power. Okay, any more for me now? Okay, so times 10 to the 8th power. Okay, so again, I'm identifying what's been given. I have lambda. Now, this is 615 nanometers, so it's times 10 to the negative 9, right? So again, this number is not between 1 and 10, so I need to make it that way. So it's now 6.15 times 10, and then so now I got to ask myself, how does making 615 to 6.15 change my exponent? Recall that my exponent got smaller, so it went down. So that means that my exponent goes up. Now keep in mind, how many times did my decimal move? 1, 2. So it went over by 2. That means this exponent changes by 2, but it goes up by 2. So it goes up by 2, so that means it is negative 7. And this is what I'm working with here for my lambda. So my lambda, so going back to my equation, speed of light times lambda times nu. I've been given lambda, but I need to find nu, so that means my new equation is speed of light divided by lambda equals nu. Okay, so I need to replace my variables with my numbers, 2.99 times 10 to the 8th divided by 6.15 times 10 to the negative 7. So now I'm actually dividing numbers, not multiplying them out. So the easiest part first to focus on is this number here divided by that. So 2.99 divided by 6.15 is 0.486 times 10. Now what's my exponent? So another rule that you may or may not remember when working with exponents is that if your base is the same and I have two different exponents, then when I'm dividing them out, I can use that same base and then I subtract the numerator by the denominator. So in this case, again, I can keep the same base. My numerator is 8 minus a negative 7. So that's really 8 plus 7, so that's 15. Okay, so that's my answer, right? So if I were to write that answer down, I would actually only get half credit. And I hope you can see why. Because this number is not between 1 and 10. So how do I make it between 1 and 10? I need to move that decimal over once. So if that decimal moves over once, then that means this number will change by 1. And I will end up with 4.86 times 10. So again, here's the question. 0.48, I went from 0.48 to 4.8. So the number went up, right? So my number went up, that means my decimal or my exponent will go down by 1. So from 15 it will go to the power of 14. And that is my answer. 4.86 times 10 to the 14th. And that is my frequency. So if you recall, that's only half of my problem, right? So 4.86 times 10 to the 14th power. That's only part of my problem. The problem was asking me to find the energy of that photon, right? The energy. So I'm not done yet. I need to use my energy equation right here. I highlighted it in green. My energy equation is the energy for the electron times Planck's constant, 6.626 times 10 to the negative 34 times 4.86 times 10 to the 14th. Okay? Let me erase this so I can have some space. So I'm focusing on these numbers right here. So I'm going to multiply those guys out. I'm working on 50, right? Yeah. Okay. So 4.88, okay, 4.8886 times 6.626 equals 32.2 times 10. And then here I have my exponent term, so that's 10 to the negative 34 plus 14, that's 10 to the negative 20, right? And then my decimal needs to move over once, so this is going to change by 1, and I go from 32.2 to 3.22, so my number went down, so my decimal point will go, or my exponent will go up. So that's by 1, that's negative 19, and that's that answer. That's the energy. Okay, well, I hope this video helped, and good luck in your study.